Greetings. This is a presentation of our thesis proposal, an automated monitoring and management system for aquaculture applications. The Philippines has a growing aquaculture industry, mainly producing fish, shellfish, and to a lesser degree seaweed. Seaweed farming plays an important role in the aquaculture business and is constantly growing. Seaweed is considered to be the second largest aquaculture farming industry in the world. Water quality monitoring is important in maintaining healthy and productive aquaculture. However, conventional methods of water monitoring brings about problems such as human fallibility, excessive time resources, logistics, and limited accessibility. In recent years, systems have been developed to resolve most of the mentioned issues through automation with the use of new technology and concepts. These existing systems, however, present problems of their own, such as a lack of salinity and turbidity parametric sensors, a dependency on wired internet connection, the involvement of excess human intervention, restriction by physical cable connection, and the lack of environmental exposure protection. The general goal of the study is the development of a water quality monitoring and management system for aquaculture applications that addresses the prevailing problems of existing systems and methods. The objectives are, first, to establish a base station for data processing, instruction, and control over the system. Second is to develop a sensor node that gathers water parameters. Third is to develop an automation node that controls the automatic water draining, pumping, aeration, and heating intervention processes. Fourth is to integrate an IoT system through wireless communication between the nodes and base station, as well as establishing connection to the internet. Fifth is to develop a web application for remote monitoring and control over the system. The project covers a system for land-based aquaculture set up in a controlled environment. The system has 3 sensor nodes, 2 of which have simulated data and 1 automation node. The system uses wireless communication through XBee modules using the Zigbee protocol. Who will benefit? First, we have aquaculture business owners, aquaculture personnel and employees, hobbyists and enthusiasts, and for general water quality monitoring purposes. The system does not cover changes in water conditions, water quality discrepancies. It is range dependent. It will only measure pH, salinity, turbidity, water level, and temperature. Only 3 sensor nodes will be deployed, 2 of which have simulated data. There is only 1 automation node. Human intervention is needed to initialize the system. A loss of connection would seize the system. The system is unable to detect faulty components and does not have backup power. This is the system overview. The system is composed of 3 subsystems: the base station, the sensor nodes, and the automation node. The base station processes the data it receives. Data is also uploaded to the server, which is then accessed through the website. The sensor node gathers parametric data and transmits the gathered data to the base station. The automation node intervenes if there are any abnormalities detected. The sensor node is composed of an XBee S2C module along with 5 parametric sensors. The sensor nodes has a one-way communication to the base station. The gathered data from the sensor module will be stored at the base station and to the PHPMyAdmin database server. For the scale and needs of the project, the star topology was chosen due to its ease of implementation, and should one end device fail, the connection with the other components will not get disrupted nor severed. This is the login landing page of our website, monitormyseaweed.com. This is the data dashboard page, where data gathered from the base station is presented along with their timestamps. This is the graphs page, where the data from the base station is converted into a line graph presentation. This is the automation node. It is composed of an XBee S2C module, a heater, an aerator, and 2 valves for water in and out. There were 7 tests that were conducted. The first test would be the sensor calibration testing. Each sensor underwent a calibration process corresponding to their requirements in order to ensure reading accuracy. The pH and salinity sensors were calibrated using buffer solutions with indicated values as reference. The temperature sensor was calibrated using water at 100 degrees Celsius, or at boiling point. The turbidity sensor was calibrated using clear water with an expected output of 0 NTU. The water level sensor was calibrated using a steel tape measure used as reference. The results of the calibration testing shows that the values acquired by the sensor in comparison with the reference values from buffer solutions or readings taken from the analog instruments are within approximate range with minor differences. Next test is the reading validation. Analog instruments were used as reference for water level and temperature parameters. For the 3 remaining sensors, a mixture sample of coffee and salt was given to the USC Water Laboratory to be tested for pH, turbidity, and salinity. The reading outputs were expected to be approximately in the same range as that from the laboratory. The result of the laboratory reading validation indicates that the sensor readings are within approximate range of the laboratory readings. Next is the Zigbee communication test. This test determines the range of communication between XBee modules. 10-meter distance increments were added per successful communication. The maximum range for outdoor scenarios with clear line of sight is measured at 120 meters, and for indoor operations with obstacles and other interferences, it is only at 30 meters. Next test is the base station testing. This test determines whether the base station can receive and send data to the database, receive data from sensors, and send instructions to the automation node. The base station was able to receive data from the sensor nodes transmitted by the XBee modules and received by an XBee module connected to the base station, which was set up to be the coordinator. The base station was able to upload data to the PHPMyAdmin database, which was then presented on the web application through the dashboard and graphs pages. Next test is the automated intervention testing. This tests the base station's manual and automatic control of the devices on the automation node. The base station has an auto feature in which, upon reaching certain sensor thresholds, would turn on or off certain devices automatically in the automation node. The components are connected to a relay switch, which controls which components should be turned on or off by providing or cutting off power to these components. The switch would take approximately 2 seconds to switch. The tank and drain valves had the longest delay due to the solenoid valve used taking approximately 3 seconds to fully open or close. Next is the web application and server connection testing. Web application was tested if it can perform remote operations such as monitoring data, adjusting threshold values, and sending override commands. The data accumulated by the base station and data received by the server was compared and should have the same data. The same data value will be observed across different access points except that of the graphs page, as data value was set up to be rounded off to the nearest ones place. This is the testing of devices such as laptops or smartphones to access the system through their own browsers. Also, the capability of the web application was tested from locations outside of the Philippines, which was simulated using VPN networks. The web application was accessible through computer units as well as mobile devices. The web application's functions, actions, and commands proved to be functional. The website was also able to be accessed from foreign locations simulated using VPNs. This is the result of the sensor node readings. Each test sequence composed of 30 data readings averaged out. 10 test instances were conducted and their average were taken. Reading reference for turbidity, salinity, pH are taken from the USC Water Laboratory. Temperature and water level readings were taken using analog instruments. The salinity parameter had the largest error at 7.95. One contribution to the discrepancy in salinity readings is due to its correlation with room temperature. When water temperature is hotter, water molecules will slightly expand, causing salinity levels to drop. Inversely, when the water temperature is cooler, salinity levels will slightly increase. The duration of the test where salinity levels were acquired lasted approximately 8 hours, during which room temperature where the sample was stored varied throughout the day, causing irregularities. The remaining sensors met the researchers' expected error of less than 5%. One factor that affects the turbidity sensor is how susceptible it is to the change of brightness in its environment. the inconsistency causing irregularities in reading. pH readings are affected by the half-life of the solution that is being sampled over time. The concentration of the solution will decrease. In this case, the coffee and salt mixture. Towards the end of the test, the acidity of the mixture slightly neutralized, hence the average pH level reading taken by the sensor is slightly higher. The water level was measured through sonar. Since level could not be verified through laboratory testing, an analog instrument was used, a seal tape measure. Human error likely contributed to the difference between the readings taken from the sensor and readings taken from the seal tape measure because it was taken through visual observation only. The temperature parameter was also not verified through a laboratory. An alcohol thermometer was used to compare this temperature taken by the digital sensor. Human error was also expected when taking measurements through the alcohol thermometer, as level indicators were incremented only by quarters, resulting in less accuracy. The main goal of the study of developing a monitoring and management system for use of aquaculture purposes were met. Problems brought about through conventional methods of water monitoring and management were addressed through the integration of an IoT system where digital instruments were implemented. Water monitoring and management devices were automated and can be controlled wirelessly and remotely through the development of a web application. Data gathered from the digital sensor node is proven to be within an accepted error range, with the USC Water Laboratory readings used as reference. Human error in maintaining a fully controlled environment accounted for virtually all of the errors the system had experienced. After further study and examination, these are the following recommendations. First is the improvement of the controlled environment setup. Second is to upgrade XP modules to that of higher range versions. Third is to equip simulation nodes with actual sensors. Fourth is to construct an automation node per sensor node. Fifth is to develop an alert system for faulty components. Sixth is to use a real-time platform such as Firebase for web development as well as implementing website responsiveness. And seventh is soldering of wired connections to prevent being loosened over time. That would be all for our presentations. We thank you.